Hello teachers, welcome to section 11-2 Curves, Polygons, and Symmetry. So when you finish this section, you'll be able to understand and explain simple closed and convex curves, including polygons. We're going to name and classify triangles and quadrilaterals. We're going to talk about the hierarchy among selected polygons and symmetries and their relation to planar figures. So let's get started. A simple curve. So notice we're going to pay real close attention to the characteristics here. A simple curve that does not cross itself. Starting and stopping points may be the same. So when it says it doesn't cross itself, it can, at the very end, start and stop in the same place. And by the way, what does that mean? Well, it's a closed curve. If it starts and stops at the same point, that's considered a closed curve. A polygon, notice, is a simple closed curve, so it has to be both of these things, that the sides are line segments, so it has straight edges. And then you can have a convex curve. Now notice what's required for a convex curve. It has to be simple and closed with no indentations. The segments connecting any 2 points in the interior of the curve is wholly contained in the interior of the curve. So for instance, if I gave you something like this, what you would try to do is draw any line segment that comes out of the curve. And you can't do that. So that means this is convex. On the other hand, concave, if I draw you a simple closed curve, there's one right there, and I attempt to draw a straight line, look, I come out of the curve, which means it is concave. And notice it does have an indentation. So that's one way to think about it. If it has an indentation, it is concave. If it doesn't have an indentation, it is convex. But I like to visualize drawing the lines. All right, let's start off with a problem right off the bat. What we want to do is classify these as simple, closed, polygon, convex, concave. And it could be none of these, okay? Now, is this a simple curve? And remember what was important about simple is it doesn't cross itself. So sure, this is simple. Is it closed? Does it start and stop at the same spot? No, it does not connect up. It's not a polygon because it's not closed and with straight edges. Therefore, you don't assume it's convex or concave, because for convex and concave, you have to be simple and closed. For a polygon, you have to be simple and closed. Okay? Next one. Does this curve cross itself? And you would say, no, it doesn't. So it is simple. Is it closed? Does it start and stop in the same position? No. Now you can't talk about polygon, convex, or concave. Is the following simple? Sure, it's simple. Is it closed? Yes, it's the first closed we've had because it starts and stops in the same point. And you ask yourself, where does it start or stop? Doesn't matter. If you pick any spot and trace it, it comes right back to it. Is it a polygon? No, it doesn't have straight edges. Is it convex? No. You know why? Because it's concave. If I pick any 2 points, or pick those 2 points and draw a line, it comes outside of the shape. Therefore, it is concave. Okay, let's take a look at a circle. Is it simple? Yes, it doesn't cross itself. Is it closed? Yes, it starts and stops at the same position. Is it a polygon? You would say no, because it doesn't have straight edges or line segments for the drawing. Okay, is it convex? It is. If you pick any 2 points, not just those two, but any two, and connect them, you're not going to come outside of the shape. So it is convex, which is not concave. You'll never check convex and concave. Now I have these typed up for you, and you can look at the results, and that should match exactly what we have. But we're not finished. I have a few more to take a look at. Why don't you pause it and see if you can answer all the questions for these 3 figures. So how'd it go? All right, this first one, very hourglass looking. Is it simple? Now, simple means it doesn't cross over itself as you're drawing it. But you know what? As I trace this thing out, right here, I have to cross over myself to get the drawing completed. So it's not simple, although it is closed. So if you put it was closed, that's true. It starts and stops at the same position. No matter where you started drawing it, you end up, when you get everything traced, where you started. Is it a polygon? No, because a polygon is a simple closed curve with line segments for edges. Convex and concave also require simple and closed to discuss them. Okay? All right, next one. So interesting shape here. It's got 1, 2, 3, 4, 5 sides. Is it simple? It is. You don't have to cross over itself as you draw it out. Is it closed? It is. It starts and stops in the same place. Is it a polygon? Well, does it have line segments for the edges? You bet, right? Is it convex? It is. If you pick any two places and draw, you don't come outside of the figure. There's no way to connect any two dots and come outside of the figure. So it's convex, which means it's not concave. Okay? The third one, is it simple? It is. It doesn't cross over itself to sketch it. Is it closed? Yes, we start and stop in the same position. Is it a polygon? It is. And I noticed I forgot to check closed. Uh-oh. Whew, sorry, y'all. That gets crazy if I don't select my pen and reselect my pen. There we go. Okay, so back to polygon. Is it a polygon? It is. Okay, so to be a polygon, you got to be three things. Simple, closed, and you have to have straight edges or line segments for the sides. Is it convex? I argue no. You know why? Because if I pick, say, this point and connect the dots, I come outside of the shape. So this little part right here is outside of the shape, and we can't have that. That means it is concave, okay? And again, the typed up version of that, which we match perfectly, there we go. Okay, every simple closed curve, so remember what that means. Simple means it doesn't cross over itself. Closed means it starts and stops in the same point. Every simple closed curve separates the plane into three disjoint subsets. Remember, disjoint means they don't have anything in common, okay? So there's the interior, there's the figure itself, and the exterior. Okay, so if you put any simple closed curve in a plane, you're going to have the interior, you're going to have the line itself, okay, and I shouldn't say line, let's call it the figure itself or the curve itself, and the exterior, the part that's not in the interior and not on the curve. All right, more about polygons here. You've heard this before. A triangle has 3 vertices and 3 sides. A quadrilateral has 4 vertices and 4 sides. Remember, what are vertices? Those are your corners, right? And you know what sides are. Pentagon has 5 vertices and 5 sides. Hexagon is 6. Heptagon is 7. Octagon is 8, like your classic stop sign. Nonagon is 9. Decagon is 10. Hendecagon is not something you hear very often. As a matter of fact, they have an asterisk there because it's not often used, but it is a thing. And dodecagon is 12. And there are names past the 12. And then an n-gon just means it has n vertices and n sides. Okay, let's talk about an interior angle. Now, this is for polygons, okay? And so the list I gave you before was for polygons. An interior angle is an angle formed by 2 sides of a polygon with a common vertex, okay? So we'll look at pictures in just a minute. Exterior angle of a convex polygon is an angle formed by a side of a polygon and the extension of a contiguous side of the polygon. Again, I'm going to show you pictures, don't worry. And then a diagonal, a line segment connecting non-consecutive vertices of a polygon. All right, so let's look at a picture here. So notice a diagonal, because I'd see it first in the picture. So here is a diagonal, it's a dashed line. Now, I can't have a diagonal from C to B because that is part of the polygon. But if you have non-connecting vertices, then you can draw a diagonal. Okay, and you'll find yourself counting diagonals for some of the homework problems. Notice that this angle 1 here is an interior angle because it's inside the polygon, whereas over here, same polygon, notice how we extended side CD, and that gives us an exterior angle. Okay, so interior angles on the inside, exterior angles are on the outside if you extend one of the lines. And then you have a diagonal that goes from one vertices to another as long as they're not connecting sides. All right, if we talk about congruent or congruent parts, these are parts with the same size and shape. So you can have congruent line segments, you can have congruent angles. So here we go. Right here, two line segments are congruent. Notice the notation. Okay, so it's got an equals with a little squiggly line. That means congruent. If a tracing of one line segment can be fitted exactly on top of the other line segment, they're exactly the same length. Okay, two angles are congruent if they have the same measure. Makes sense, right? All right, so notice here it says segment AB is congruent to CD. If we were to pick up AB and set it right on top of CD, they would fit perfectly. That's the definition they gave you for congruent. Notice the little lines over it. To note congruence, you can put a single line for those are congruent. If you had more than one line segment that was congruent, you could move on to double lines to denote those are congruent. So there's different notation to represent congruent. Look at these congruent angles. Again, notice the notation. It says angle XYZ, or ZYX, I read that backwards, is congruent to angle RQP. So XYZ is congruent to RQP. They are both 108 degrees. How about a regular polygon? All sides are congruent and all angles are congruent on a regular polygon. So the side lengths are all the same, and every angle is the same. So regular polygons can be really neat. A regular polygon is equilateral and equiangular. So same angle, same side length. And notice we have pictures of a regular pentagon. Remember, pentagon means it has 5 sides, and a regular hexagon, which has 6 sides. How about triangles? Okay, a right triangle, you know what that means, is it has a right angle. Remember what right angle is? It's a 90-degree angle. So a right triangle has a 90-degree angle. An acute triangle, all angles are less than 90 degrees. A triangle in which all the angles are acute. So remember, an acute angle is less than 90 degrees. So that is saying that this angle, that this angle, and this angle, all of those are less than 90 degrees, where an obtuse angle is a triangle that has an angle that is over 90 degrees, and of course less than 180, and then there's your obtuse angle right there. Okay, I'm sure you've heard these terms before. You just need a bit of a reminder. A scalene triangle is a triangle with no congruent sides. Notice the notation again. With the one line and the double line and the triple line, it's trying to tell you that none of these side lengths are the same. So scalene means no side lengths are the same. An isosceles triangle, on the other hand, has 2 congruent sides. So in this particular triangle, the left side and the right side are congruent, whereas the bottom side may or may not be congruent. Okay, in this picture I assume it's not because it's not even marked. An equilateral triangle has all 3 sides are congruent, which is also going to have all 3 angles are congruent. But isosceles, just at least 2 of the sides. Notice it does say at least. You know what that means? That an equilateral triangle is also an isosceles triangle. But neither of these are scalene, right? The scalene means none of the sides are the same length or congruent. What about a trapezoid? Well, it's a quadrilateral with at least one pair of parallel sides. So you'll notice this side and this side are parallel. There is no information about the other 2 sides. It could look various ways, but we have 2 parallel sides in a trapezoid. Now, a kite is a quadrilateral. Remember, that means it has 4 sides. So anytime you see quadrilateral, that means it has 4 sides with 2 adjacent, remember, next to each other is adjacent, sides congruent, and the other 2 sides also congruent. So notice The longer sides here, they're adjacent to each other. Those are congruent. And then the other two are congruent as well, but not necessarily all four congruent. But if they were, it would still be a kite. Okay? So, again, at least two adjacent sides are congruent and congruent for a kite. And there's more. There's an isosceles trapezoid. What does that mean? Remember, a trapezoid means that you have two parallel sides, and there they are. Isosceles means the leg lengths are the same. So notice that notation with a single line across, that means those are congruent sides. What's a parallelogram? It's a quadrilateral, four sides, in which each pair of opposite sides are parallel. So in this picture, these two sides are parallel, and then these two sides are also parallel. So that's a parallelogram. And a rectangle is a parallelogram. So all rectangles are parallelograms because two opposite sides are parallel, but you also have the 90-degree angle. Then you could have a rhombus. What is a rhombus? It's a parallelogram with two adjacent sides congruent. So again, what makes a parallelogram a parallelogram? Well, this side's parallel to this side, okay? And this side's parallel to this side. But what makes it a rhombus is that adjacent sides are congruent. Would that not mean all four sides are the same? I believe it does. Okay, square, a rectangle with two adjacent sides congruent. Okay, so it is a rectangle. It is. So a square is a rectangle, always. A square is a particular subset of the rectangle set with two adjacent sides congruent. Now, what's a rectangle? A rectangle is a parallelogram with 90-degree angles. Okay, and this side is congruent, and turns out all four sides are congruent, like a rhombus. Hey, a square is also a rhombus. You'll have some homework where you have to deal with that. All right, how about hierarchy among polygons? You may want to refer back to this later when you start doing homework. But a polygon, okay, you could break down into all of those shapes we talked about earlier, but let's just focus on triangles and quadrilaterals, okay? Now, polygons break down into triangles, and triangles break down into scalene and isosceles. But remember how I told you an equilateral is also an isosceles triangle, because an equilateral has three congruent sides, and an isosceles triangle has at least two. All right? Similar things happen within a quadrilateral, and it gets a little bit more confusing. But a quadrilateral can be broken down into a kite and a trapezoid. So remember, a trapezoid has two parallel sides. I am attempting to draw two parallel sides. Here we go, two parallel sides, and how these others are connected can be however, okay? A kite is a quadrilateral with two adjacent sides congruent, and then the other two adjacent sides congruent, okay? But that could give you a rhombus. You remember what a rhombus is? It's a parallelogram. Notice rhombus fits under parallelogram. It's a parallelogram where all four sides are congruent. Now, a trapezoid, remember, it can break down into an isosceles trapezoid. And an isosceles trapezoid is not the one I have in green here, but an isosceles, you have your two parallel sides, but the legs are congruent. So this side is congruent to this side. Now, a rectangle is also an isosceles trapezoid and also a parallelogram, right? Because parallelogram has opposite sides are parallel, and that is true for a rectangle. And then extra about a rectangle is you have the 90-degree sides. It's also, again, an isosceles trapezoid, which is also a trapezoid because it has the parallel sides and the two legs are congruent. And then finally, a square seems to fit in every single category. A square is a rhombus, is a kite. A square is a rectangle, is an isosceles trapezoid, is a trapezoid, and it's also a parallelogram. So refer back to this later if you get confused, please. All right, how about symmetries? Line symmetries. Mathematically, a geometric figure has a line of symmetry L if it is its own image under a reflection in L. So notice the line symmetries here. We have a vertical line symmetry in figure A, and then we have these two others. And so ignore the two others for a minute. Just focus on the vertical. If that were a mirror, do you see that it just reflects through? Same thing, we have a line symmetry this way, it would reflect that way, and then it would reflect that way. So you could do that several different ways. Whereas B, and that is a kite, right? So it's a quadrilateral, it's got 4 sides. These sides look to be congruent to these sides. For them to be truly symmetric and have that symmetry along there, it would have to be a kite. And again, if I put the mirror right there, you see it reflects through. This is the star only in a star quilt. Okay, that's what it's just telling you is the star only. You're not looking at the rest of the package there. It's just saying look at the star only. Look at all those lines of symmetry. If you were to fold, again, if you were to fold down this line, notice this would just fold right on top and everything would line up. And think about that. With line symmetry, you could just fold it like it was a piece of paper. And if that's the case, the figure will line up on top of itself. Look at the boat. Okay, if I folded a piece of paper right down this line, then the left side of the boat would land right on top of the right side of the boat. Those are line symmetries. So I have some examples here. How many lines of symmetry does each drawing have? Now the drawback of these examples is the lines are already drawn for you, and you really just need to count the lines, but you would need to be able to draw these lines yourself. So think about reflecting through. Notice if we drew a line right down the middle here, if I could get my pen to work. Okay, I think I got my pen to work now. What I was trying to do is highlight this line for you. Again, if you reflect through there, right, it would be a line of symmetry. Same thing here. So this is number 2. And then number 3, 4, 5, 6. All of those are lines of symmetry. So the answer to this question is, it is 6. Okay. Let's look at the next one. Notice again, the line of symmetry is already drawn. It is just 1, but I think you could see that. There's no way we could draw any other line, not horizontal, not at an angle, where this A would reflect through. So A just has a vertical line of symmetry, and that's it, and that is just one line of symmetry. Whereas maybe a 0, or you look at this as like a racetrack, notice that we could draw vertically or horizontally. So we have 2 different lines of symmetry here. Then I've got one more picture for you. Look at that. The Z. What do you think? Well, there's no lines drawn on it, right? So obviously there's no lines of symmetry. But think about, I mean, every way you draw it. If you drew it vertical, that's not going to reflect over. If you drew horizontal, it's not going to reflect through. It's like the opposite. So that figure there has 0 lines of symmetry. Now, that's not the only type of symmetries we could talk about. We could also talk about rotational symmetry or turn symmetry. So a figure has rotational symmetry or turn symmetry when the traced figure can be rotated less than 360 degrees. So not all the way around. About some point, the turn center is that it matches the original figure. So like this triangle, we could just rotate it. You see that, 120 degrees, and A would land on top of B. B would land on top of C, and you see how that works. C would land on top of A. But you could also do it, not just 120 degrees, but you could rotate 240 degrees where A landed on top of C, and C landed on top of B. So that's got 2 different symmetries right there, rotational symmetry. Notice here this unusual shape almost looks like leaves. This, again, is another 120 degrees rotation, but it's not just 120 degrees. It would also work for 240 degrees. Now, you can't do 360 because that's all the way back around. Everything has 360 degrees rotational symmetry, right? So that doesn't count. So for these, we're supposed to figure out the rotational symmetry. So help me out. What are you thinking? Do you recognize that symbol? That's like for a Plymouth vehicle, right? So it's kind of neat. So we know that if we could rotate, say, this corner to this corner, right, we would have what we need. How do we figure out the degrees there? Well, let's think about this. We're taking all the way around 360 degrees, right? How many sides do we have? Let's see, you have 1, 2, 3, 4, 5 sides. So if we took 360, ooh, my pen is not behaving right, and divide that by, that's not me, that's my pen. I'll have to fix that, I'm sorry, by 5. So 360 divided by 5, that's going to give me 72 degrees. Well, look at their answer. You got 72 degrees, 144 degrees, 216 degrees, and 288 degrees. What is that coming from? Well, the first rotation, again, let's see if my pen will work, is 72 degrees. It's not. And the second rotation is 72 plus 72. That's 144 degrees. And then another 72 would make that 216 degrees. And then another 72, that's the 288 degrees. So all of those are considered rotational symmetries of this figure. All right, what about the next figure? And I think you should pause it and go ahead and make your list and come back and see if we match. All right, how'd it go? So, you know, if I rotate from here to here, okay, how many degrees is that? So what you likely did is you looked at it, and this has got like figures like 1, 2, 3, 4, 5, 6 different divisions, right? Not sides at all, but different pieces that match up. So if I took 360 and I divide that by those 6 sides, that gives me that 60 degrees. And then if I rotate from here to here, that's going to be 120 degrees. And then if I rotate from here to here, that's 60 plus 120 plus another 60, right, is 180 degrees. You know, from top to bottom is 180. We know that anyway. And then 180 plus another 60 will give us 240, plus another 60 would give us 300. So this is likely the list that you came up with. Hopefully it is. So remember, it's not just one rotation, but you could rotate further around. Okay? And then the last question I have for this type of question is, look, that's the Chevy symbol, right? What kind of rotational symmetry do we have here? Can we rotate like from the top to the bottom? Can we rotate sideways, 45 degrees, 90 degrees? No, I'm just thinking, well, here's what I'm thinking. We can go from, if we rotate 180 degrees, this corner is going to land right here on that corner, right? Again, my pen is misbehaving, or I am, I don't know. So this corner is going to land on this corner. And that's a 180 degree rotation, and that is exactly what that answer is. You have something else called point symmetry. Any figure that has rotational symmetry 180 degrees is said to have point symmetry. So our Chevy symbol that we used just a minute ago had point symmetry because it was 180 degrees. And also, let's go back, our star also had point symmetry because it's 180 degrees, but notice our Plymouth symbol did not have point symmetry because 180 degrees is not on that list. So all of these have point symmetry, and notice they just rotate around a point. Okay? Classification of figures by their symmetries. Geometric figures in a plane can be classified according to the number of symmetries they have. We can use lines of symmetry and turn symmetries to define various types of quadrilaterals normally used in geometry. Consider a triangle described as having exactly one line of symmetry and no turn symmetries. What would that look like? And so you see here it's got one line symmetry. Notice this is an isosceles triangle, right? And no turn symmetries. Now my 30-minute time slot is about to run out. And I have 2 homework examples I want to show you, and I am positive they're going to take more than that 30 minutes. So I'm going to come back for a part 2. It's going to be teeny tiny, but worth the coming back because I go over some homework problems. If you have any questions about this or any other sections or homework, please let me know. I hope you have a wonderful day.